Uh, all can see my screen, right? Everyone can see my screen, right?
Yes,
Yes.
yes, we can see.
Yeah.
Yeah. Akanksha, you can go ahead and start the presentation.
Hello, everybody. We are from Group 7. Today, we are going to discuss regarding our machine learning fourth project app. And in our group, we have got Revant Reddy, Avinash Reddy, Rishita Reddy, myself, Akanksha, Darshak, Shakira, Tabassum, Vikas, and Zanglu. Um, Now, coming to our machine learning app, the first topic that we are going to discuss regarding this is bagging assemble algorithm. Bagging, short for bootstrap aggregating, is an assemble machine learning algorithm designed to enhance the performance and robustness of predictive models. The key principle of bagging lies in creating multiple subsets of the original training dataset through random sampling with replacement. Now, these subsets are only known as bootstrap examples, and then they are used to train individual base models. The final prediction is generated by aggregating the prediction of these base models, typically through voting, which is called classification, or averaging, which is called regression. The later part would be explained by one of my teammates. Thank you.
So I'm going to
Rishi.
explain. Yeah.
Yeah.
So stacking algorithm assemble learning. Stacking, also known as stack generalization, is an assemble learning technique that combines the predictions of multiple base models using another meta model, often referred to as a stacker or meta learner. Unlike bagging and boosting, which involve parallel or sequential training of base models, stacking aims to leverage the strengths of diverse models by training a meta model to make predictions based on the outputs of the individual base models. Here is a high level overview of the stacking algorithm. Base models train multiple diverse base models on training data. These can be models using different algorithms or models with different hyperparameters. Base model predictions use each base model to make predictions on the validation sets or a subset of the training set not seen during training. Create a stacking data set, combine the predictions of the base models along with the original features to create a new data set. Each base model's prediction becomes new features in this stacking data set. Meta model train a meta model on the stacking data set. This model takes the combined predictions of the base models, has input features, and learns to make the final prediction. Final prediction, use the trained meta model to make predictions on new unseen data. Key points about stacking. Diversity of base models. It's essential to use diverse base models to ensure that the assemble captures different aspects of the data or model types. Meta model selection. Common choices for the meta model includes linear regression for regression problems or logistic regression for classification problems, but more complex models like neural networks or gradient boosted trees can also be used. Cross validation. Stacking often involves using cross validation to train base models and create the stacking data set, ensuring that the stacking models is evaluated on data not seen during its training. Multiple layers. Stacking can be extended to include multiple layers of base models and meta models, creating a more complex ensemble structure. Stacking can be a powerful technique which, when implemented correctly, as it allows the ensemble to benefit from the strength of different models and adapt to the intricacies of the data. However, it also requires careful tuning and validation to avoid overfitting and achieve optimal performance. And and the next part will be continued by one of the teammate.
Yeah. Thank you, Rishita. Now the next topic is Ansible learning using AdaBoost classifier. In this, Ansible learning refers to the technique of combining multiple machine learning models to create a more robust and accurate predictive model than the individual model themselves. AdaBoost, short for adaptive boosting, is a popular Ansible learning algorithm that focus on the combining the outputs of weak learners to build a strong learners. In context of AdaBoost, a weak learner is a model that performs slightly better than a random chance. Here are the key steps in using AdaBoost for Ansible learning. So the first one is initialization. Here we assign equal weights to all training instances. Base model training. Train a weak model and often decision tree with limited depth on the training data. Adjust instance weights to focus on misclassified instances. The next one is compute model weight. Calculate the weight of the weak model based on its accuracy, updated weights, increasing the weights of a misclassified instances so that they have a higher chance of being selected in the next iteration. Repeat, iterate steps 2 to 4 for a predefined numbers of iteration or until a stopping condition is met. Then the final prediction, combine the prediction of all weak models, giving more weight to the models that performed well during training. AdaBoost effectively adapts to the difficulty of instances in the dataset, assigning more importance to misclassified instances in each iteration. The final model is weighted combination of weak models where the weights are determined by the performance of a weak model. Ansible learning using AdaBoost often results in a strong and accurate classifier. It is widely used for binary classification and can be extended to multi-class classification on regression problem. The algorithm is known for its simplicity, versatility, and the ability to handle a variety of base learners. When implementing Ansible learning using AdaBoost, it's crucial to choose an appropriate weak learner, tune hyperparameters, and carefully monitor the number of iterations to prevent the overfitting. When coming to the next topic, this is a clustering. That means clustering using k-means algorithm. Clustering is nothing but it's a type of unsupervised machine learning technique that involves grouping similar data points into clusters or segments based on their inherent similarities. The goal is to maximize the intra-cluster similarity and minimize the intra-cluster similarity. Unlike supervised learning, clustering does not rely on labeled output and the algorithm discovers the inherent patterns and structures within the data. Then what is the k-means algorithm? K-means is one of the most widely used clustering algorithm. It partitions as a data set into K clusters, where each data point belongs to the clusters with the nearest mean. The K in K means represents the number of clusters desired. The algorithm iteratively refines its clusters by assigning data points to the clusters whose mean is closest to them and then updating the clusters means. The process continues until convergence where the cluster assignments no longer change significantly. Key steps in the k-means algorithm. Initialization. Randomly select the k data points as initial cluster centroids and the assignment. Assign each data point to the clusters whose centroid is the nearest, typically using eliciting distance. Update centroid. Recalculate the centroids of each clusters by taking the mean of all data points assigned to that cluster. Reassignment. Repeat steps 2 and 3 until the convergence are a predefined number of iterations. The algorithm aims to minimize the sum of squared distance between the data points and their assigned cluster centroids, known as inertia or within cluster sum of squares. K-means has some notable characteristics and consideration. Sensitivity to initial centroids. The algorithm final results can depend on the initial selection of centroids. Different initialization may lead to the different solution. Deterministics. Despite the sensitivity to initial centroids, the algorithm is deterministic and meaning that with the same initial condition, it will coverage to the same solution. Assumptions of spherical clusters. K means assumes that the clusters are spherical and equally sized. It may struggle with non-spherical or uneven sized clusters. Scalability. K means is computationally efficient and scales well with a large number of data points. K-means is widely used for various applications, including customer segmentation, image compression, and document clustering. Choosing the right value of k, number of clusters, that is nothing but a number of clusters, is often a subjective task and requires the domain knowledge or additional techniques such as elbow method and Silhouette analysis or class cross validation. The next concept will be explaining by Akanksha. You can take from here.
Thank you so much for that. Now I'm going to explain the topic, which is hierarchical clustering. It is nothing but it's a type of clustering algorithm that builds a hierarchy of clusters. So it's nothing like a group of clusters that builds together. So it starts with each data point at a separate cluster and then iteratively merges or divides cluster based on their similarities until all data points belong to a single cluster or a predefined number of clusters is reached. Now, the result of this hierarchical clustering is a tree-like structure called dendrogram, which usually represents the hierarchy of clusters. There are mainly two types of hierarchical clustering, which are agglomerative and divisive. Agglomerative hierarchical clustering is a method which begins with each data point as a separate cluster and each iteration merges the closest pair of clusters until only one cluster remains. Divisive hierarchical clustering. It means that all data points is in a single cluster and each iteration divides the cluster until each data point in its own cluster. The other type of data sets that can be used is single linkage or single link. It's nothing but a method for measuring the similarity between two clusters in a hierarchical clustering. It defines the similarity between two clusters as the minimum distance between any 2 points, one from each cluster. In other words, can you scroll it down, please? The distance between two clusters is determined by the closest pair of data points, one from each cluster. Mathematically, when this clustering is explained, if you can see the equation, d of x comma y represents the distance between clusters, where x and y and d of a and b represent the distance between data points of a and b. And then the single linkage between clusters x and y is given by d of a text single x of y is equal to minimum a in x, b in y, d of a of b. Single linkage tends to produce elongated clusters and is sensitive to noise and outliners. It is computationally efficient but can suffer from the chaining effect where clusters are extended due to single point connecting them. Can you scroll the page a little bit down? Now, coming to the complete linkage or complete link, it is another method for measuring the similarity between two clusters in hierarchical clustering. It defines the similarity between two clusters as the maximum distance between any 2 points, one from each cluster. In other words, this can be explained as the distance between two clusters, which is determined by the farthest pair of data points, one from each cluster. Now, this one is mathematically defined as if cluster of d of x and y represents the distance between clusters x and y and d of a and b, it represents the distance between data points a and b. Then the complete linkage distance between clusters x and y is given by d of text complete x and y is equal to maximum a in x, b in y, d of a and b. Complete linkage tends to produce more spherical clusters and is less sensitive to outliners than single linkage. However, it can be sensitive to noise and tends to create compact but spherical clusters. It is also computationally efficient. Both single linkage and complete linkage are valid approaches for hierarchical clustering, and the choice between them often depends on the nature of the data and the desired characteristics of the resulting clusters.
Okay, thank you, Akanksha.
Thank
Now
you.
we are done with all the definitions which we are gonna implement, which we have already implemented in our code. Okay, so these are the definition for all the things. Let me just come back to the code. I have already executed Jupyter code in my terminal, and let me just go take you back to the code here. So this is our code. I already ran it once. Let me run it again, all the cells. Okay, we have already got all the results here. So, okay, yeah, coming to the data set, we have already taken the data set, which is the nursery database. This is the following data set, which is in JSON format. We have taken this one, nursery JSON. Nursery database was derived from a hierarchical decision model originally developed to rank applications for nursery schools. It was used during several years in 1980s when there was excessive enrollment to these schools in Jumblajan and Slovenia, and the rejected applications frequently need a objective explanation. The final decision dependent on three subproblem: occupation of parents and child's nursery, family structure and financial standing, and the social and health picture of the family. The model was developed within expert system shell for decision making DEX, and this is about the data set which we have taken. When coming to the features, these are the features which we have got in the data set. So this is nothing but a parent feature, has nursery, and form feature, children feature, housing, finance, social, health, and class. There were total 8 features in our. These are 8 features are nothing but the columns, and 1,000 like 12 uh, 12,960 instances. These are nothing but the rows which we have got in our data sets. It's a pretty big data set which we are implementing here, and a possible value of categorical values. You can see here the parents, the usual, and has. These are the possible categorical columns which we have got in our data set. So here these steps says that loading data set. As we already know that we have to load the data set, which is nursery.json. Here we are including all necessary packages, pandas, JSON, sklearn, whatever we have learned in our classes. All these are necessary here to. That's why we are importing everything from here. A simple inputter, and as you can see, everything decision, random forest, k neighbors, classifiers. Okay, here in this step you can see that data equals to json dot load. Here we are loading the nursery dot json into the data object here, this variable. Okay, we are storing it in a data variable. Okay, we are converting the JSON data into Panda data frameworks. Okay, when coming to that, here this steps says the data pre-processing. Here we are missing the handling values, handling missing the values. This is the following code for it. And as you can see, inputter equals to simple inputter, strategy, most frequent. So all these things will be like whatever we have done previously, the same things are happening over here. And encode categorical features, data equals to pd dot get dummies. These are the categorical features. Data comma columns equals to, these are the like categorical values which we have got 8, right? These are the 8 values here. And split the data set into the features and target variables. Here we have taken as x and y, and we are doing it so far. And split the data into training model. This is the following code for it. X train and x test, y train comma y test, then equals to train underscore test underscore split equals to, this is the following one. And functions to evaluate the model. These are the functions to evaluate the model. We are evaluating the model over here. So here evaluate underscore model. Here we are sending the model x text and y text. So these are the following code for it. And you can see it. And the bagging Ansible algorithm. So from here, since we have already discussed about the what is this one, bagging Ansible algorithm, you can see here we are defining the base classifier decision tree in this case. Okay, base classifier equals to decision tree classifier. Inside it, random state we are taking as 42, and define the bagging classifier. Bagging underscore classifier equals to a bagging classifier. Then inside it, inside this function, like base classifier in estimators we are taking as 10, and random state we are taking as same as 42, and we are training the bagging classifier here. Okay, bagging classifier dot fit, inside it we are training the x and y variables. Okay, and accuracy precision recall f1 equals to evaluating the model, which is nothing but the above step. Okay, and here we are printing the Ansible learning with bagging classifier accuracy, precision, recall, and F1 score. You can see the values over here, which we have got as a result. Accuracy 0.99 something, and precision 0.72503 something. Like we have got these values over here. And then coming to the next concept, stacking algorithm, Ansible learning. So in this, we are importing all necessary libraries from this sklearn, Ansible, and sklearn tree, sklearn Ansible linear model. And here we are defining the base classifiers, where base classifiers equals to this thing, decision tree and random forest. And in this step, we are defining the meta classifier underscore. This is the one we are taking as 42 everywhere, and define here in this step we are defining the stacking classifier, and in this step we are training the stacking classifier same as the above one. And the same thing, like we are doing each and with the different model we are performing the same accuracy, recall, and f1 score. Okay, so here we are printing the result for accuracy, precision, recall, and f1 score for this one, stacking algorithm, Ansible learning. Okay, as you can see here, the accuracy and precision value and f1 score, when you compare the above one and the below one, you can see the difference over here in the outputs. You can see the minimal differences, but the numbers are different. Okay, so when compared to when coming to the Ansible learning using Adabus, the other one, Adabus classifier, we are importing the Adabus classifier from sklearn Ansible. Here we are defining a weak learner, that is nothing but a base estimator. In this case, a decision tree. Base classifier equals to this one, and we are taking maximum depth as 1, and here defining the Adabust classifier with a weak learner. Okay, Adabust underscore classifier equals to Adabust classifier base learner n estimator. We are taking 50 and 42, and here we are training the Adabust classifier over here, and same as the above one, we are printing the accuracy, precision, recall, and f1. Okay, f1 score. You can see the difference over here. Like we have got a major difference when compared to the accuracy. You have got 82. Here you have 99, 55. So you can see the a lot more difference between them. So this is about the Adabust classifier. When coming to the clustering k-means algorithm, here we are importing NumPy, Matplotlib, PyPlot, and sklearn datasets. From sklearn dataset, we are importing the make underscore blobs. Okay, since we have to show the blob, like these things. So and k-means, we are importing k-means. So this one here we are generating a synthetic data with the 3 clusters. Okay, data comma true labels equals to make blobs. These are the values we have taken, and creating a k-means model with 3 clusters over here, and we are fitting the k-means model to the data, and get the cluster labels and centroid. Predicted underscore labels equals to k-means dot labels, centroid equals to k-means dot clusters underscore centers. So we are plotting the true data, and k-means clusters, k-means clusters results here, and plot dot figure equals to these are related to this one, like we are gonna show over here in the graph, and 10,6, and plot true data points. So these are the data points we have taken, where it is and edge colors is k, S equals to 50, and label equals to true labels. Okay, as you can see here, yellow one represents the true labels, and if you can see here, we have mentioned the color also, edge colors K, and let me just show you. Plot K means predicted labels. Okay, in this we have taken plasma, CMAP as plasma, edge color as K, and a marker as S, label as K means production. So this means in this case, if you can see here, we have this one that represents this color, K means production, and plot centroids, plot dot scatters centroids. So as you can see, the color is red, centroids. The red into mark is nothing but a centroids. We have placed a marker called as X here. As you can see, we have placed centroids everywhere. X, X, X. Okay, and S equals to 200. Label equals to centroids. So here PLT. This is nothing but we are plotting everything over here to show the differences in the graph. Okay, feature 1 and feature 2. You can see the difference. You can this shows the representation like feature 1, feature 2, and the colors and everything. Okay, true colors versus labels. K means predictions. Okay, and coming to the hierarchical clustering, single linkage and complete linkage. Here we are importing NumPy as NP and matplotlib PLT, and so we are importing dendrom and linkage from the cluster hierarchy, and we are importing make underscore blobs from sklearn's dataset. We are generating a synthetic data with the 3 clusters here, the same thing which we have done above. Performing the hierarchical clustering with the single linkage, this is the following thing we have done, and performing this hierarchical clustering with a complete linkage, this is the following code for it, and plot the dendrograms for the both linkages. So this is we are plotting the figures, subplot and title. So we are plotting the title also over here. You can see the hierarchical cluster single linkage. This one represents it, the single linkage, and yeah, and this one represents the complete linkage. This one, and we are showing everything plot. So this is nothing but we are installing the necessary library Fuzzy in order to show the next cell results. We are installing it, and as you can see here, Fuzzy C means clustering. Here we are importing NumPy as NP and matplotlib plot and skfuzzy, and we are generating a synthetic data with the 3 clusters, the same as we have taken there, and applying Fuzzy. C means clustering, where centers U, U0, D, D. These are the variables we have taken, and fuzzy.clusters.c means. So we have assigned for each of the variables which we have taken, and extract the clusters membership from the membership matrix. So we are extracting the cluster membership from the membership matrix over here in this step, and we are plotting the data points with the cluster memberships over here. We are plotting everything: scatter, title, X label, Y label, legend, all these things. As you can see here, cluster center represents a cross arrow, cross mark, as you can see here. And this one represents varsities, the yellow ones. So this is all about the machine learning concepts which we have implemented in our application. And these are the following running results. I'm gonna upload all the running results for this assignment, for the submission. And yeah, and we have used the JSON data for a panda, like to have used here in this application. Um, think that's it about that's all about all our application. Uh, thank you. Thank you, everyone. We are
Thank
done
you.
with our presentation. Thank you. I think we can stop the recording.